From beginning. So this is exactly what it's going to look like on December 21st, by the way, people. So make sure you have your scopes out. Actually, Andrew's going to cover that in more detail. We already coordinated. Thanksgiving, at least for me, is not quite over because I still have leftovers. But also, I have a lot of thanks to give. And this is sort of the time of year when we do that. And it is our last meeting of the year. So I want to give credit where credit is due. And there's a lot of credit to go around. First to Lewis, who's been both treasurer and webmaster. We have a spectacular website now.
Yeah.
There's a lot of things you can do with it. There's more you can do with it than I have even figured out how to do with.
But the best thing, if I may say so, that can be done with it is people seem to be doing things to make it better themselves. Trust me, most of the goodness is not due to me.
Well, it's a fabulous site, and I also know from personal experience what a thankless job being treasurer is. So I will thank you this year, and for every subsequent year you have that thankless task. I have thanks to Jeremy, who's brought us really 12 fantastic programs this year and has already got programs set up and meetings set up for 2021. Never have to worry about what's going to happen. He's on top of it, and also really working in the background on a lot of other things for the club. Andrew, thanks for all your work on observing. I'm sorry we haven't had enough nights that we could go out, and the pandemic has sort of put a cramp on things, but it's been fabulous what we've done nonetheless. And I love your presentations at our meetings. In organizations, a lot of times people say the best job is immediate past president, because once you're done being president, you're sort of done with the organization. You feel like you've given it your all. Here's Joe Lamb coming back as a past president and going, I have some more time on my hands. And scope rentals is a tough job, and he stepped forward and said he'd be willing to help us out, and I really appreciate his doing that. Brian, who couldn't be with us tonight, is our welcoming chair. He coordinates the new members, gets the new member packages out, and again, an intake issue that I never have to worry about. Barry Johnson's our go-to person on light pollution. I actually had a guy call me just this week out of Delaware and tell me he had a problem. And he really needed some sort of light pollution advocacy to be put in touch with, and I put him together with Barry. I was glad I had him as a resource. Then we have our own personal club, Mr. Science. Al Amperti, the only thing he's missing is the bow tie. And Al's just generally around always whenever we need somebody. He's our liaison to the Night Sky Network, and probably, Al, if you wore all your pins at once, you would not need a bulletproof vest. Bill's another example of a past president who continued to be involved. We have a podcast now. Lou, you could probably tell more about the podcast because I know Bill's not on yet.
Yeah. So, well, again, I'm an executive, so my job is always taking credit for things that other people do. And so this would be another example. Bill came up with this idea for us to do a podcast called Pod Astro, and we've done three episodes so far, and it's a combination of Bill and I just yapping about all things astronomy, and we've had several guests now, and we hope to make it into a regular thing. And the first episode, I believe, is on the site right now, right? So
yep, it's up.
Give it a go.
It's up. Roy.
And one other thing.
Yeah.
I'm sorry.
It's okay.
You can listen to the podcast not only on the website, but you can listen on, iTunes and Spotify.
Oh yeah, you can download it now, right?
Yeah. So you listen to your car or stuff.
Yep. Very cool. Roy was doing door prizes when we had real meetings, and thanks to Roy. Roy's also been involved in other ways in the club, but that he was the guy who was there selling the tickets, and hopefully it won't be too long before he's back behind the counter doing that again. Nate has been our camping czar, has organized our trips to Cherry Springs, of which we had a few this summer, notwithstanding the pandemic. And I'm glad he's able to organize those, because the kind of camping I do is I set up my tent and then I stay down the street at either Frosty Acres or one of the other motor inns. And then there's Janet, who's sort of our own Supergirl. Uh, Janet makes being president very, very easy. She puts out this fantastic newsletter. She's handled outreach. She's been secretary. She's organized Women of DVAA. Clearly a superhero of DVAA, and really keeps this club running smoothly, and keeps me honest. Mike's been able to cover for me a couple of times this year, and I appreciate it. He was at the Miro meeting when I couldn't be there. And of course, turns out Janet was there and Al were there. So DVAA had 3 representatives, which was great. And he stepped forward in other ways. And of course, Lou, who was asked to handle astrophotography, took a committee chairmanship and has already had a couple of seminars, webinars. It's been great. We have like 160 members. And when you see this next list of people who got involved in this fabulous auction, 1 in 7 members is active in the club. And I mean, really active. And it's probably closer to 1 in 5 because of people who've shown up at some of our outreach events. That's terrific. You hear of a lot of organizations where there's mostly members and maybe, 5, 10, 15 people who are active. We've got dozens and dozens of people who have given of themselves to work for the club, and it's fabulous. It really, I have to tell you, it makes my job extremely easy. I know it's not hard at all. These are the candidates coming up. Elections are coming up. They will be online through the website. For officers for 2021, you'll notice that Michael Tucker has stepped forward to be secretary, which we appreciate because terms are limited to 3 years. They're 1-year terms, but we're limited to 3 successive terms. And Jan has, of course, taken on another role as vice president, which we really appreciate. The bylaws were amended last year to expand the number of members at large we can have, and very excited to have Tracy join us as a second member at large. Thanks for stepping forward to all of you. We also decided to go, and again, I have to give credit where credit's due. Jeremy and Janet really hatched the idea of an editorial board. And so we're going to start with an editorial board so we have more people involved in the newsletter so it doesn't fall unfairly on any one person's shoulders. And again, really excited to see people like George stepping forward, Tom stepping forward, Dana stepping forward to help us out. It's great to see all this involvement, and it's just great. I love it. This is the agenda for the business meeting. There's a more detailed agenda is going to be available on the website. If there's something, some of the agenda is dictated by the bylaws. If there's something in particular you would like to see us address at the business meeting, and any members free to attend, and it will be a Zoom meeting, which unfortunately means there will be no donuts unless you bring your own donuts into your own house. But if you want something on the agenda, and this applies to officers, committee chairs, and members, if there's something you want me to add to the agenda, just shoot me an email. Here's my contact information. The easy one is president@dvaa.org, or just use my regular email. They both go to the same place. And the last thing, since Brian is not here, I want to welcome 2 new members, Matthew Wallow and Herbert Garvin. Because I'm right now on the screen with my PowerPoint presentation, I can't see if they're on the call, but welcome. You've just joined a very vibrant community, and we're delighted to have you here with us. So with that in mind, we'll go to the reports from the officers. And since and I always in my mind's eye picture us sitting at Radnor, and we have that bar on the side, and it's usually Brian with the camera, and then I think next would be Lewis. So Lewis, you're up.
Sure. Could you give me screen sharing? Jeremy?
Done. You should be good to go.
Okay, great. So, okay, can you see my screen okay? So, we're in renewal period. We have 167 members today, and a third of those people are already renewed. That means I think 110 people still need to renew. You should have received an email that tells you how to renew. Everyone's received one of those, right? Someone say yes.
Yes.
So anyway, here's the way a renewal happens. I'm actually going to renew for my wife in front of you. Firstly, you go to DVAA, and it's going to get to a login screen, log in, and then it's going to have this lovely little icon up here. And if I hadn't practiced,
We don't see that at all.
I don't know about you,
We
but all
just
we
see
see
your
is the
background.
moon.
yeah, that's why I'm sorry. That's why I was confused, saying why is it not showing?
You picked the wrong window to share.
Yeah, I think we're just seeing your secondary monitor, Lou.
Okay.
If you hold up your credit card to the camera, we can help you with it.
Okay. Well, I'm looking. I'm now. I can't get back to on share mode to pick the new thing. Could you
You
on share
stop
me?
share, right?
Yeah, on share and then reshare me.
There you go. I just stopped your sharing.
Okay, and selecting a window. It is not showing for some reason it's not showing the browser. Hold on a second. You would think I'd have this stuff down since I am a professional.
Must be on a Mac.
It's definitely not on a Mac.
Well, didn't Bill Gates do that Windows demonstration that time and the computer crashed right in the middle of it?
Yes.
Yes. So this is literally not showing my browser. Oh, there it is. Okay. Sorry. That was really painful. Okay. So I've logged in as Marie Anchamet, my wife, and there was a pop-up that's saying, hey, you need to re-register. Also, there is an icon up top. So I'm going to re-register her as a regular member. Her information should all be correct, but it's worthwhile checking it out. And then next, and then I'm not going to uncheck any of her interests and stuff, but those can be played around with. And then finally, I'm going to just finish and proceed to pay. And it is literally this simple, right? I'm not going to, if you don't mind, type the credit card in front of you. But the point.
I'll give you $100 if you do.
Yeah, I'm sure you would. And but the point is, renew membership. It shows the invoice and everything. It shows credit card information. Oh, do you want us to retain your credit card information online? I'm going to submit payment. Oh, expiration date has already passed. Very sad. So the point is, you don't have to watch me filling out this last page, but the point is that you can certainly register in just a minute or two. It's very, very, very easy, and I'd appreciate if everyone does this so that I don't have to track you down in June, which is our traditional time for saying, gee, a bunch of people haven't paid.
And you can actually, because as I discussed before the meeting began, I had thought that through the website you could also do the subscriptions to astronomy or sky and telescope. So I got to this process and did not pay. So now when I log on, I get a reminder that I have to make the payment. So if you just want to renew and not pay immediately or something like that, it'll remind you. It'll eventually lock you out if you don't pay, but you don't, if you don't happen to have your credit card when you re-up, you can go grab it later, go back in, log in, and it'll remind you, make the payment at that time.
Perfect. Excellent.
Okay, unshare.
Unshare.
Only in 2020 is unshare a verb, transitive. Let's see, in my mind's eye, next would be Roy, but we don't have door prizes. That would be neat if you could do door prizes at Zoom meetings. Somebody should come up with that.
We just
So
did an auction. So
yeah,
Put them online.
yeah, there you go.
I mean,
So
storefront.
I'm going to first go to in random order. Lou, do you have anything for photography? You're muted and your video's off thoughtfully. And Lou's not there. He'll come back. He'll text me or something. That's what he usually does. Janet, I'll throw it to you.
He said no
Okay.
in text.
I just wanted to add to what Harold said about the auction. It went really smoothly. It looked like people had a lot of fun to me bidding. It looked like fun to bid. We had so many people that participated, with I think 43 total people, and a third of them were non-members. So people that heard about us through the publicity that was done. And within 5 days, everything was paid. And about 2/3 of the items have actually now been delivered. So we're making really good progress. Jeremy, I still see the daub in your background there. But maybe
Price is Right girls here. Yeah.
by the next time we get together, I think everything will have been delivered. So thank you everybody for participating and having a great time.
All right. Thank you, Janet. And thanks for really corralling that together. That was, you were sort of the irresistible force that, see, I don't have the physics background, but you kept it going and I really appreciate that. Lou did text me and say he has no report. I don't think there are any other committee chair reports. So Andrew, I know there's something happening later this month. I don't think it's a meteor shower.
yes, no, there isn't. It's a surprise. Well, it's not really a surprise. Let me share my screen. Oh wait, I can't. I'm in the middle of the presentation. No peeking. So there we go. So for those of you who don't know, my name's Andrew Hitchner. I'm the DVAA observing chair, and this is my observing report for the December 2020 meeting. So Harold mentioned that we coordinated, and it actually took me a really long time to think about what to talk about for this month. And I pride myself in not having repeated any presentations. I think in like the three or 4 years that I've been doing this, I don't know, it's been a while. But I didn't want to do just like the regular, winter observing, wear your coat outside report. So I was looking for something special, and there's something happening this month, which we've already noted. And I wanted to talk about those events in general. So we're going to talk about conjunctions, joining words, phrases, and clauses. No, I'm just kidding. We're going to talk about astronomical conjunctions, much more interesting. I was never good at those other kinds of conjunctions. So we're going to talk about astronomical conjunctions. There is a formal definition. It's not just two objects getting close. There's some preliminary events that need to go on. And this is a conjunction between the Moon, Saturn, and Jupiter at the Very Large Telescope away in Chile. The Moon is, of course, the brightest object there. Then we have Venus and Jupiter. Although the most striking thing to me is look where the Milky Way is in this image. It's just amazing to me. So, of course, down in Chile, that's where it would be. So what is an astronomical conjunction? And this is really going to be a quick crash course in positional astronomy, which, to be honest, hurts my head a little bit. So I'll try and explain it as best I can, although I'm sure many of you know much more about it than I do. So an astronomical conjunction occurs when two objects have either the same right ascension or the same ecliptic longitude. And I'll talk about that on the next slide. Now, this can happen between planets in our own solar system, and then it can also happen between an object in the solar system and a more distant object, such as a star or maybe an interesting dark sky object. So I mentioned right ascension and ecliptic longitude. So remember, there are many coordinate systems, but there are two main ones that we use for describing where in the sky an object is. Most of us are familiar with the coordinate system on the left, the equatorial coordinate system with right ascension and declination. So if we took the longitude and latitude of the Earth and just expanded it out into the celestial sphere, then we would have the equatorial coordinate system. So we have right ascension going along here, and then we have declination going along there with the point up top of the north celestial pole and the south celestial pole. So this, of course, would be, it's very close to Polaris, not exactly, but very close. And then we have the ecliptic as this line going here, of course, the line where the planets and sun follow as they go along the sky. Now, the other coordinate system for conjunction is in the ecliptic coordinate system. This is a little more obscure, so, and these look very similar, but if you look at the ecliptic line over here, it's not really at zero, right? It's not the zero, right ascension, declination is the equator. In the ecliptic coordinate system, now the ecliptic is zero. So I don't really like these, although these pictures are the best that I could find, because the Earth kind of, you know, Africa kind of has this, in South America, they're not tilted. In reality, the Earth would be kind of tilted, right? But notice that the ecliptic is now the 0 point, the reference point, whereas in here it was kind of off axis. And now the North Pole is not the North Celestial Pole around Polaris, it's now actually around Draco or so. So of course, it's never going to be zenith, depending on where you are, right? Zenith is going to change. So you're not really going to have zenith unless you're actually at the celestial pole to be one of these two coordinate systems. So zenith you can't really go by. But just wanted to point this out. Now, luckily, when we're talking about planetary conjunctions, which is what we're interested in, we're only worried about this coordinate system here on the left with right ascension and declination. So remember, a planetary conjunction is when two planets have the same right ascension. Now, if they also have the same declination, we can have a few different phenomena happen. We can have a transit where the closer object appears smaller than the further object, okay? We all know like transits can happen between moons and their planets and so, or even between other planets. We can have an eclipse where one object moves into the shadow of the other, or we can have an occultation, which is kind of the opposite of a transit, where the closer object appears larger than the farther object. Interesting note, when we have a solar eclipse, we're really talking about a combination of eclipse and an occultation, because the moon is slightly larger than the sun in that case. So interesting note. So when we talk about conjunctions, we also need to talk about superior and inferior, because they're different kinds of conjunctions. So an inferior conjunction is when the orbit of a planet, or an inferior orbit, let's say, is when the orbit of a planet lies within the orbit of the reference planet, which is then called the superior planet. So let's start with our frame of reference from Earth, right? We have the inferior planets of Mercury and Venus, right? Because their orbits are closer to the sun than ours. And then we have the superior orbits with Mars, Jupiter, Saturn, Uranus, and Neptune, and of course, Pluto. Now, of course, with many things in physics and astronomy, this all changes depending on your reference point, right? So if our reference point was, let's say, Jupiter, then the inferior planets would be Mars, Earth, Mercury, and Venus, and the superior planets would be Saturn, Uranus, Neptune, and Pluto. Now you know why my head was hurting as I was making this presentation, but just hang in there. So there's a superior conjunction where the inferior planet is on the opposite side of the sun as you. And then there's an inferior conjunction where the two planets lie in the same line of sight. So I have this nice picture here, right? So we're only going to worry about the Earth because that's where we live. We like the Earth. So we have the inferior orbit closer to the sun than us, and then we have the superior orbit farther away than us. So a inferior conjunction is when that inferior planet is between us and the sun, and then we have a superior conjunction when that inferior planet is between, or is on the other side of the sun than the reference point. So one more thing we want to talk about is triple conjunctions. So this occurs when two planets meet each other 3 times in a very short period. And you can think, well, how does this happen? Well, of course, with some of the planets, such as Mars, Jupiter, and Saturn, you can get these points where the orbits or the movement of the planets in the sky seem to be going in the right direction and seem to be going in the opposite direction as the sun. So this occurs when the first conjunction is in prograde, then the second conjunction, short while after, is in retrograde, and then we have a third one again in prograde. So this can be between two inferior planets. It happens very frequently between Mercury and Venus. However, we usually can't see that because Mercury and Venus it usually happens when they're very close to the sun from our point of view. It can also happen between superior planets such as Jupiter and Saturn, right? So when we have a conjunction between Jupiter and Saturn, that's called a great conjunction. And when we have a triple conjunction between Jupiter and Saturn, that is the greatest of conjunctions. There is no better conjunction than a triple conjunction of Jupiter and Saturn. I didn't make this up, I promise. So why do we care? To be honest, astrologers know a lot about this. Why do I care as an astronomer? Right? So there's, of course, a great conjunction between Jupiter and Saturn on December 21st, 2020, where they will be about 0.1 degree, a tenth of a degree apart at time of conjunction. So that is at the exact moment when they have the same right ascension, they will be 0.1 degrees apart. Is that going to be the time that we are able to see it? Probably not, but they're going to be very close. They're going to be so close that it's going to look like about the same object in the night sky. Now, as I said, I was trying to figure out, what can make this really interesting. I just point out a bunch of facts that I had to read 10 times to understand. Why is this interesting? Well, there's another notable great conjunction that you have all heard of, but you've probably not realized was actually a conjunction of Jupiter and Saturn. And of course, I'm talking about the Star of Bethlehem. So I was thinking, I kind of wanted to make something Christmassy because it's December, right? And, the Star of Bethlehem's one of the biggest astronomical events out there related to Christmas. And it just so happens, a nice coincidence, that this is a very similar event to what we will be able to see in December 21st. So there's a lot of debate to what the Star of Bethlehem was, assuming that, we're getting told the correct story. And there's three leading theories. One, it could have been a comet, although those happen a lot, really. They're not really quite rare. This would have been a really rare event. It could have been a supernova or a nova, a new star. Those are a little less rare. It could have also been a triple conjunction because according to the story, the wise men saw two astronomical events. One when they were on their way to Jerusalem, when they were going to go see King Herod, and another on their way to Bethlehem. And these were very similar time periods. And then the third, they probably didn't record because they weren't observing at that time. So the Star of Bethlehem could be explained by a triple conjunction of Jupiter and Saturn. And again, there's two planets that are going to be so close to each other that they're going to look like just one bright star. So this is going to be exactly what's going to happen. What we're going to see isn't a triple conjunction. It's just a single conjunction on the 21st. But it's very similar to what the wise men might have seen as the Star of Bethlehem. So just to tie it all in there. So thanks for sticking with me on that one. And I will turn it back over to you, Harold.
Thank you. If I had hair, it would hurt. That's great. I think the one thing about this upcoming conjunction is that we will see just as much disinformation between now and December 21st as we do, the typical email we get every summer that Mars will be as big as the moon. So be prepared for that, and armed with Andrew's information, just start talking superior and inferior conjunctions, and when their eyes glaze over, you will have done your good deed for astronomy.
And be sure to read. I can't tell you how many articles I was reading only to find out that it was then later going to describe to me how I would be feeling on the day of conjunction because it was an astrological. So just be careful when you're reading about it. But no, be sure to go out and see it. It will be pretty neat.
Yep. Well, hope for clear skies. Jeremy has a great guest for us, and I would just ask everyone to do what most of you have done, which is kill video, kill mute yourselves and let Jeremy and Emmanuel take us away.
All right. Thanks, Harold. It's been my pleasure to do programs for this year, and we're already getting some programs scheduled for next year. So you'll be hearing about those fairly shortly. All right. So tonight, very pleased to have Dr. Emmanuel Sean. He's joining us from Lawrence Berkeley National Laboratory, which if you are good with your geography, you realize is out in California. So he's joining us from the West Coast. So probably the sun is just setting now over there. He is a Chamberlain postdoctoral fellow over there. And I actually got to know him from another astronomy club where he gave a presentation a couple of months ago. And it was really nice, so I figured I better have him here to talk to us. Let's see, so Emmanuel did his PhD at Princeton University, so he's actually been in the area before. He worked with David Spergel, who's one of the giants in cosmology. He did his undergraduate work at the École Normale Supérieure in Paris. Emmanuel, in addition to all of his research, he's active in public outreach. So he's done presentations to a number of groups, including libraries, elementary schools. He's taught some courses at the college level. He's also led some outreach projects, and one that I thought was interesting was one with a Near Space Balloon Project that he helped out with at Princeton University. And he's also been active in public observing programs. And also he told me he's an active amateur astronomer, so he's working on a 10-inch mirror right now. So Emmanuel, you've actually made more telescopes than many of us in the room right now. And let's see, we've got 50 people total, including Zoom and YouTube. So please join me in welcoming Emmanuel Sean, and his talk will be called A Cosmic Shadow Theater. Welcome.
Great, thank you so much. Thanks a lot for this very kind introduction. And I should, disclaimer, I should clarify that I have technically made 0 telescope currently. I think I'm close to finishing that mirror, but famous last words. Yeah, so I hope you can see my slides. I'm really excited to present to you these results. And so this is a project that I led and whose results were posted online a few months ago. And so this is really fresh. And this project is about hidden shadows of the gas around galaxies. And the idea is the following. When you think about galaxies, you may not suspect it, but around the stars that you see, there's actually a whole lot of diffuse gas. And that diffuse gas is very important for a number of processes that I'll explain. But that diffuse gas, because it's so diffuse, is basically invisible. It doesn't emit enough light for us to see. And so we wouldn't know about that gas, except for the fact that if you could grab this galaxy and this gas and put it in front of a bright light, that gas would cast a shadow. And so this is what this presentation is about. All these images are shadows from the gas around galaxies. And so as I said, these are very recent results, and so I'm pretty excited about them. I think they're also exciting because they are the most precise images of those galaxy shadows ever made. So no one has ever seen more precise such images, which I think is cool. These shadows and their properties actually tell us a lot about the gas, not just where it is. And this has important implications for a number of astrophysical questions that are important. And so this is what I'm going to tell you about. And finally, I should say that the method that was used to generate these images, and which I'll explain, will be familiar to all of the astrophotographers in the room. So I think that's kind of cool. But before getting started, I thought I should say a few words about what I do as my work. And so I'm a cosmologist. Cosmology is the astrophysics on the larger scales that we get to observe. And a number of problems that I work on are these 3. Gravitational lensing of galaxies. And so that's the fact that if you look at the image of a galaxy, that red dot here, those images can get distorted by the presence of foreground masses. I also work on gravitational lensing of the cosmic microwave background, and I'll say a lot more about what that is. But it is this this funny looking speckled image, and that one too gets distorted by foreground mass, and so you can measure gravitational lensing from it too. And finally, the third topic that I work on a lot is the large-scale distribution of galaxies in the universe. So how they're clumped how they clustered. And all these three things tell you a lot about the history, the composition, the evolution of the universe. But that would be for another talk. And I should say, while I'm technically a professional astronomer, I'm also an aspiring amateur astronomer. And I think this is something really cool about astronomy, is that I learn a lot every time I talk to amateur astronomers. And so I love DIY projects. Jeremy mentioned this GoPro camera on a weather balloon to take photos of the Earth from near space. I like to put my camera on improbable DIY mounts, take photos of things with more or less success. And I'm hoping to finish my 10-inch amateur telescope mirror anytime now. But one thing I still wanted to say is that in astronomy, we're very lucky because it's a field where amateur astronomers actually advance the state of the art of scientific results. And so I just wanted to highlight one paper that I really like. No need to read all this in detail, but basically this person, Donald Bruns, during the 2017 solar eclipse, using amateur astronomy equipment, granted very high-end equipment, made one of the most precise measurements to date of gravitational starlight diffraction, which is a test of general relativity. So basically, you can advance science by being an amateur astronomer. And so I wanted to thank all the amateur astronomers in the room for contributing to this. And finally, to thank you, I wanted to point out those two websites that you may or may not be familiar with. These are the cornellarchive.org and the NASA Astrophysics Data System. And what these are is those two websites are databases on which basically every single astrophysics publication is available publicly. And so you can look for any paper with state-of-the-art research. You can search for author, publication date, title, you name it. And the flip side is that if you produce results that you think push the state-of-the-art of astronomy, this would be a good place for you to post them. And the results I'm going to present tonight are the result of work that was publicly funded. And so naturally, the results are publicly available. So these are the two links to the papers. If you're interested, feel free to take a look. So moving on to the actual topic, those cosmic shadows, I thought I would start with motivation for why we care about. And to explain this, I wanted to start with an analogy that hopefully makes it clear. So it's getting dark outside, but if instead of going out and looking up at the stars, you were an alien looking down onto Earth, this is what you might see. And so you see a bunch of bright spots, bright speckles that basically trace cities. And so if your goal as an alien was to try to understand where human beings are on Earth, perhaps for the purpose of world domination or any other reasonable goal you may have, a natural guess you may make is that where there's more light, there's going to be more people. And if you look at an actual map of the galaxy population, sorry, the people per population density on Earth, this is what you see, where green and red corresponds to more people. And so what you see is that that guess, that light traces population, is not a bad guess at all. It's pretty good, except in some cases. So for example, in some places, you might see that there's not as much light, but there might be a lot of people. And in other places, you might find that the light is very concentrated into bright spots, whereas the population is actually a bit smoother and more diffuse. And it turns out this is exactly what happens in the universe. And so astrophysicists say that light is basically a biased tracer of the mass. And in particular, the light is more concentrated than the mass distribution. So to show you how this happens in the actual universe, here's an image from a computer simulation of the sky. And so here, every bright dot is a galaxy. And again, this is not a photographic image of the sky. This is a simulation, so simulating the universe on a computer. And if in this image you ask yourself, where is most of the mass located, you might naively think that it would be in those bright specks. But the actual answer is the following. So you see those sort of shocking images where most of the mass is actually on those very diffuse extended blobs. And So that's the key motivation for this project. And the fact that this is somewhat of a problem because of all of the ordinary matter in the universe, the thing that makes up you and me, computers and telescope, only 5 to 10% of it is inside of stars. And the vast majority of the ordinary matter, all the rest, the 90 to 95% of the ordinary matter in the universe, is actually in the form of this diffuse, effectively invisible gas. And the fact that it's effectively invisible is the reason why you probably have never seen a true image of the sky that looks like this. This gas does not emit light enough for us to see. And so this has been called the missing baryon problem, which really means just missing ordinary problem. And it's a problem for a number of reasons. One, because as astrophysicists, we'd like to study the majority of the mass in the universe, not just the 5 to 10 lucky percent that are inside of stars. So that's a problem. We'd like to know where the mass is. And the other reason why it would be really nice to be able to see this gas is that this gas, its location and its thermodynamic properties, so how hot it is, for example, hold a number of clues about galaxy formation. And the reason that is you might wonder, why is that gas so far away from the center of galaxies? And the answer is because there are processes inside the galaxy that push the gas out. And it turns out we don't know too much about these processes, but if we could tell exactly how far out the gas is, we would know how powerful those processes are. So these are the motivation for this project. It would be really nice if we could detect this hidden invisible gas to learn in particular about galaxy formation, but also about other fundamental physics questions that we care about in cosmology. And the reason for this is, if you want to learn about those mysterious components of the universe, one of the best tools we have is to try to find where mass in the universe is. And it's very hard to make progress on this if you don't know where those 90 to 95% of the mass is. So this is the goal. And the question now becomes, how do we detect that gas? And here's a random image I took one evening. And on this image, you might ask yourself, how do I detect the fact that there is gas in the atmosphere? And if you look with your eyes, you can actually see that there is gas because something is blue. And here something is orange. And the reason it is this way is because there is a backlight far away, here about below the horizon. And that backlight is the sun. And so light from the sun goes through that gas in the atmosphere. And something happens to that light when it goes through the gas. And this is called scattering. And so basically, if you have a bright backlight behind the gas, you can light up that gas and know where it is. And so this is our idea. This is what we would like to do with the gas around those galaxies. So the idea is simple. You'd like to have a backlight behind the galaxies such that you could see the shadow of the gas. And the only problem with that in practice is that it is hard to fly a source of light far away behind a galaxy, then turn it on, then wait for millions of years for the light to travel all the way to you. And so the question is, might there be a backlight already there in the universe? And the answer is, we are actually very fortunate that there is such a backlight in the universe. So please don't worry about this confusing diagram, which represents the evolution of the universe since the Big Bang. So on the left here is the Big Bang, and on the right here is us today. And so if you look towards the left, you see all of those galaxies. But if you look even further right after the Big Bang, you see this source of light that's called the cosmic microwave background. Cosmic because it is there in every direction that you look. Microwave because we see it today as microwave light. And well-named background because indeed it sits behind everything else we see. So again, this is us. If we look towards galaxies, those galaxies are backlit by this cosmic microwave background. So the question now is, can we use this backlight to see the shadow of the gas around the galaxies? And the idea is the same as when you have a watermark on a banknote. If you just look at the banknote, you don't see it, But if you hold that banknote against the light, then all of a sudden the shadow appears and you learn about that watermark. Nature has been kind to us, and we have this cosmic backlight ready to use. Here's a little bit more information about this cosmic microwave background. So this is an all-sky map of the cosmic microwave background taken by the European satellite Planck. And there would be a lot to say about this image. And I'll just say that since it is the first light we see after the Big Bang, all these red and blue dots that you see actually are a baby picture of the universe. And from studying this image, we have actually learned about half of all the things we know about the universe, how old it is, how much matter, how much light is in there, its composition, its evolution. And the story of the study of this cosmic microwave background is just incredible. And it could be a whole presentation and more in and of itself. But for the purpose of this presentation, it's really just a backlight. In fact, if I could have been picky and asked for a backlight of my choice, I would have asked for it to be completely uniform, but you don't get to choose. And to give you a sense of scale, each of the red and blue spots here, which are basically brighter and darker spots, depending on the direction you look at, each of these blobs is about a degree in size, so 2 full moons. Okay, this is the cosmic microwave background. And so what we would like to do is zoom in on this map at the position of the galaxy and try to see if the gas causes a shadow. But then you might ask yourself, what does a shadow of a galaxy look like? So this is the same schematic as before. So here's a telescope, the Atacama Cosmology Telescope. And I'll say much more about this very soon. And we look up into the sky and we look in the direction of galaxies. And again, the cosmic microwave background, this microwave radiation, is here as a backlight for those galaxies. So when photons or light from the cosmic microwave background travels through those galaxies and the gas around them, this light, as you can see in this schematic, is affected. And this is what I'm talking about when I talk about shadows of the gas. And it turns out different things cast different shadows, and from different shadows, you may learn different things. So what I mean by this is that if I just hold my hand in front of the sun, what I'll see is probably just a black outline that will just tell me about the shape of my hand, where my hand is. But it turns out the shadows of this gas in front of the CMB contain slightly richer information. And in fact, there are 2 different effects that were predicted. These are called the kinematic and thermal Sunyaev-Zel'dovich effects after Rashid Sunyaev and Yakov Zel'dovich, theorists who predicted this effect in the 1970s. And those complicated names just refer to the physical process that causes the shadow. And it works as follows. The reason the light from the cosmic microwave background is affected by the gas is because the little particles of the gas are moving. And they're moving for 2 reasons. One, because they're part of galaxies that are themselves moving. And so this is called the kinematic Sunyaev-Zel'dovich effect, kinematic for bulk motion. And this shadow tells you about the gas density and where it's moving. So already more than just the shape of my hand. I know where it is and I know where it's moving. The second type of shadow is due to the second type of motion of the particles in the gas, which is just thermal motion. So anything that's hot has thermal agitation, particles are moving. And when the cosmic microwave background photons see those moving particles, they are affected. This is the thermal Sunyaev-Zel'dovich effect. And it's useful because this different sort of shadow tells you different information, tells you about what's the temperature of the gas or what's the thermal energy. So this is kind of neat. We don't just have one shadow, we have 2 shadows. One tells you about how much gas there is and where, and how fast it's moving. The other shadow tells you about how hot it is. So that's kind of neat. If we use that cosmic microwave background as a backlight, not only will we see the gas, but we'll learn interesting stuff about it. So yeah, let's just do this. And to do this, as I said, you need to zoom in on that map of the cosmic microwave background. And to do this, you need a fairly high resolution. And so to do this, we use data from the Atacama Cosmology Telescope. And this telescope sits on the top of the Cerro Toco mountain in Chile. And so let's go there. And the reason to put the telescope up there is because the altitude is extremely high, about 5,000 meters or maybe 15,000 feet. And importantly, the air there is extremely dry. This is a desert. And the dryness of the air is very important when you want to look up at microwave radiation. And so short of going to space, this is one of the best sites on Earth where you could put such a telescope. And the Atacama Cosmology Telescope is this one. As you can see, we have friends on top of the mountain, the polar bear and Simon's array and class, and soon a new neighbor that I'll talk about. And if you take a look inside that weird conical shape, what you see is that this white cone that you saw was actually a ground screen to protect the telescope from heat from the ground. And inside that ground screen is our telescope, the ACT telescope. So this is an off-axis Gregorian with a 6-meter primary mirror. So the light from the sky bounces off of this mirror into a 2-meter secondary detector, and then back inside the telescope into our detector. So this is very fast optics. And to give you an idea of the resolution, arc minute is about the resolution of your naked eye. But here we're not looking at optical light, we're looking at microwave. And so arc minute resolution is actually very hard to achieve in the microwave. In fact, you need a 6-meter diameter telescope to be able to do this. And something I just wanted to say a word about, because I think it's just incredible, is the detector technology that goes to detect those microwaves. So these are superconducting transition edge bolometers. And what that means is basically a piece of silicon, like you may have in your smartphone, that is then cooled at about 1 degree, less than 1 degree above the absolute zero. So this is not freezing cold, this is freezing cold and then about 300 Celsius colder, or 500 Fahrenheit colder than freezing cold. And at this temperature, quantum mechanical magic happens, and your piece of silicon turns into an extremely sensitive thermometer. And so when the microwave light from the sky hits it, you get to measure the brightness of that light. So an incredible machine, but just as incredible are the people who designed it, built it, operated it, and analyzed the data from it. And so this is an image from our collaboration meeting last year, back when you could stand this close from a person without worrying. You might recognize me in the back, and this is just an incredible bunch of superstars. And okay, so when you have these people, when you have this instrument, let me show you the kind of images you can make. And so again, Planck, this is a cutout from that map from the European satellite, which mapped the whole sky. And you can see that when you zoom in, the image is grainy, noisy, and you can clearly see the resolution. And when you add data from the Atacama Cosmology Telescope on the part of the sky, what you get is something like this. And so you can see the image is much more smooth. So the resolution has been increased a lot, and so has the sensitivity. So the noise has gone down. And so that's great. You put in all this effort, you got this telescope up there, you collected this incredible data, and you made this beautiful map. So now you can ask, where are the shadows from our galaxies? And you do see some bright dots here. And these indeed are galaxies. But the shadows should appear as dim spots. And so they should appear as bright blue dots as opposed to red. And so these, unfortunately, are not shadows from our galaxies. They're emission from some of our galaxies. And so you look at this map and you don't see the shadows. And so as a beginner researcher, your first conclusion is, well, too bad, you know, it sounded fun, it was worth trying, but it just doesn't work. But then when you talk about it with your colleagues, the answer, I tried, but it doesn't work, is not good enough. People want to know, okay, it didn't work, but why did it not work? Was it expected? Should you have known that it wouldn't work? Is it surprising that it didn't work? So it's not good enough to just say, well, I tried and it didn't work. Okay, moving on. And so how do you answer this question of, should you have detected it? The way you do it is you run calculations for how large you think your signal should have been, how large your noise should have been, and you compare the two. And so these are computer simulations. And so here what you see is those degree-sized blobs of that cosmic microwave background, that backlight. And here on the right is a simulation with only those shadows that I care about. And you can ask, okay, should I be able to see those small dots inside this map? And to answer the question, you look at the size of the signal. And for the cosmic microwave background, you see 300, whatever unit that is. Whereas for the signal that I care about, you see something that's about 100 times smaller. And so, okay, I was looking for a signal that's 100 times smaller than the thing that confuses it, my noise. And so it makes sense that by looking at the map, you shouldn't be able to see those shadows. So as a beginning researcher, your next conclusion is, okay, it made sense that we shouldn't have been able to detect it, and that's too bad, and that's the end. But of course, I think all the astrophotographers in the room know that you don't just stop there when your noise is high, and there are things you can do when your noise is too high. One of them is stacking. So for example, if I take an image of the moon and I'm not happy because it's very grainy, I can take many other images of the moon and I can average them together. And the idea is that the signal, the moon, will stay there, but the noise fluctuations will go down. And it turns out there's a very good rule of thumb, and that's the following. If your noise is about 100 times larger than your signal, then you need to stack a number 100 squared of images. And that basically applies to pretty much everything in photography and astrophotography. And so in principle, what I would need to do is to take 100 squared or 10,000 images of the galaxy I care about and average them together. And then I should be able to detect my shadow. Except in this case, if I take all these images of the same galaxy, my noise is always the same and it doesn't go down. So what I can do instead of taking 10,000 images of one galaxy is to take one image of 10,000 galaxies and average them. So I take this map where each of my galaxies is invisible, and I cut a little patch around each of the galaxies, and I average them together. And if I do this 10,000 times, I should be able to see my signal. Now the question is, how do you find 10,000 galaxies? That seems like a lot. And in my field, when you need a lot of galaxies, you always do the same thing first. You ask the BOSS, and BOSS, Baryonic Oscillation Spectroscopic Survey. What this acronym means doesn't really matter. What matters is that it's an experiment using a telescope at the Apache Point Observatory that observed the 3D position of 400,000 galaxies. So this is way more than I need in principle. And to show you those galaxies, I've made this visualization. So we are sitting here at the center of this image, and the telescope has been looking in two directions, that direction, and every time the telescope saw a galaxy, a dot was put on this visualization. And in the background, I placed the image of the cosmic microwave background. Because you know the galaxy positions in 3D, you can actually turn around. And so you can look around at your galaxies in every possible angle. And in particular, what you can do is you can measure the image of that microwave background at the position of each galaxy and average them together. And that's how you do the stacking. So I'm going to show you the result of this stack. And for now, what you see is only one image on one galaxy. To give you a sense of scale, if you were to zoom in on the very central pixel of this image and look at that pixel with the Hubble Space Telescope, you would see the galaxy like this. So this is the typical galaxy that I'm looking at. And so that galaxy is very small. The resolution of the instrument is represented by that inner white circle. So basically, every point will map to a circle of about this size. And the outer white circle here shows you the extent we expect for the gas, how far we think the gas should be. And again, if you look at only one galaxy, like on this image, you don't see anything special at the center. or within this circle, you basically just see noise. And so what I'm going to show you now is a video of adding more and more galaxy. And so this video lasts only 4 seconds. And I hope it shows well over Zoom. I'll show it a few times. But those 4 seconds you should really think of as a year and a half of my life. So that's like very, very sped up. And to show you what happens, at the start, you see nothing, just specks of noise. And at the end, you do see a dark spot at the center, pretty much where you expected the gas to be. And so I'll just replay it slowly. And you can see how when you add more and more galaxies, you see noise fluctuations, but progressively, the center becomes darker and darker. And that's when the shadow of the galaxy starts to come to life. And so this is how we detected the gas around those galaxies by stacking images of about 400,000 galaxies. And you may notice something in this image, the fact that not only there's a dark shadow, but at the very center, there's a bright spot. And that bright spot is not the shadow from the gas that I'm hoping to see. It's actually light emitted by the galaxy itself. So to summarize the measurement, we use data from this Atacama Cosmology Telescope, as well as the European Planck satellite, to measure images of that microwave backlight. And we stack them at the position of 400,000 galaxies. And again, this is what an individual galaxy would look like if you were to look at it in the optical. It would fit in the very central pixel of these stacks. Now, what you see is 3 different images. And if you remember, I described that there were 2 different sorts of shadows. And so one is this kinematic SZ, this very faint bright spot you see at the center is actually the gas density profile around those galaxies. And this image may not look very impressive for an astrophotographer, but this is actually the most precise image of this effect ever made. So this is the best image we have of this. And again, this is the other type of shadow where you see the dark spot at the center with the bright emission at the center, and with that bright emission subtracted with the process that does this. And so this is the key result of this measurement. We have been able to take all those galaxies, those 400,000 galaxies, and put them in front of a bright light and detect the shadow from the gas around those galaxies. And something that's quite striking is just how far out the gas is extended compared to the size of the galaxy. So every time now you look at the sky and you see a galaxy again, you shouldn't underestimate that galaxy. It has a lot of gas around it. And finally, as I said, those measurements actually tell us useful stuff, not just where the gas is, tells us how hot it is. And this gives us insight on galaxy formation and the processes that are responsible for making this gas so extended. And so there's a lot of people in the galaxy formation community who are excited about these results and want to include them in their models. And finally, we also have used those measurements to learn about where the mass is, and therefore those gravitational lensing and other exotic effects. This was a measurement I was really excited about, and I should say it's really only the beginning. The reasons for this is the following. The Dark Energy Spectroscopic Instrument, DESI. DESI is a spectrograph that sits on top of the 4-meter Mayall telescope in Kitt Peak, Arizona. And what it is basically is a bigger version of the BOSS experiment I just told you about. And so this is also an instrument for that I'm part of its collaboration. And I was fortunate enough to be sent there to participate in the commissioning of this instrument January a year ago. So this is the telescope. The instrument has been on the sky and collected data. This has been somewhat delayed by the coronavirus, but we're basically back on the sky. And within a year from now, the data from this instrument, the number of galaxies will be such that the precision of the shadows will be 3 times improved. And so we're really, really excited to be able to analyze this data. So that's one reason this is only the beginning, just more galaxies. The other reason this is only the beginning is better cosmic microwave background light. And so this is a rendering of the Simons Observatory, which is going to be the new very large neighbor on the top of the mountain in Chile that I showed you. To give you a sense of scale, this is a normal sized door that a person would go through. And so this is an extremely large telescope. And if you look inside, this is a cross Dragone telescope. And the way it works is that the light comes from the top, bounces on the primary, the secondary, and then reaches this gigantic cryostat where the detectors are. And again, to give you a sense of scale, the focal plane of the instrument, the size of that cryostat, is about the size of a king-size bed. And so the boost in sensitivity we'll get from this instrument will further improve our ability to measure those shadows by a lot. So let me just summarize what I talked to you about. The first thing to remember is that when you see a galaxy out there in the sky at night, you should really think that most of the mass is not in those visible stars. Most of the mass is in the gas around those galaxies, and that gas is extremely diffuse, extremely extended. So little galaxies, but a lot of gas around it. And how do we see this gas? We can see it like a watermark on a banknote by putting a backlight behind it. And the universe has been kind enough to provide this backlight, the cosmic microwave background, which is the first light from the Big Bang. And by doing this measurement, by doing a stacked measurement on many, many, many galaxies, we are able to detect those shadows. And so if you're interested in further details, you can see all the scientific papers in those two links. And so I'll stop there, and thank you very much for your attention. And of course, if there's any question, I'll be really happy to try to answer.
Okay, so if you have a question, thank you very much, Emmanuel. If you have a question,
Harold, we can barely hear you.
You might have
moved my
changed your
mic. I picked my mic up. If you have a question for Emmanuel, please let us know and speak up.
Yes, hi, it's Mike Tucker. I have a question. Is this gas found mostly around spiral galaxies, or would it also be found around ellipticals and irregular galaxies?
Right, that's a good question. So one thing so this measurement was around elliptical galaxies. And the reason for this is because those elliptical galaxies are typically at the center of galaxy groups, so more than just one galaxy. And as a result of this, there's a lot more gas because there's all the gas shared from all the galaxies in that galaxy group. And so it helped us to be looking at elliptical galaxies, so there was more gas we could see. In principle, there's also a lot of gas around spirals, but given our sensitivity currently, it's harder for us to be able to image that gas.
Thank you.
I have a question. Has anybody correlated the existence of gas around galaxies to the existence of active galactic nuclei?
Yeah, that's an excellent question. So if I go back to this image, this is exactly what we're hoping to learn about galaxy formation. So basically you can run, so as I said, those were simulated universes on a computer. And on your computer, you can change how many active galactic nuclei there are. And what these are, I'm sure you know, but for people watching us, is supermassive black holes that sit at the center of those galaxies that swallow some of the gas and then expel it out. And depending on how many active galactic nuclei you have or how many supermassive black holes, the gas gets pushed out farther out or closer in. And so that's actually one of the key things we want to learn about with these measurements, by measuring how far out the gas is, learning how many active galactic nuclei there are. And this is actually one of the best ways of getting at that question.
I have a question. This might sound a little naive, but is there any way to detect dark matter using the technique, since dark matter holds the galaxies together?
Right. Yeah, that's a very good question. And actually, for those galaxies for which we've just measured the gas, we actually know where the dark matter is. And the reason we know where the dark matter is has to do with this other effect that I didn't really talk about, this gravitational lensing effect. So dark matter is basically invisible because it does not interact with light. It does not cast a shadow on the backlight, but what it does have is mass. And so if you look at background images of galaxies and you look at how they're distorted, you learn about how much mass there is. And such measurements have been done for those same galaxies. And what we find actually is that the gas is way more extended than this dark matter. And the reason for this is basically those active galactic nuclei that Harold just talked about. And so just how far out the gas is extended compared to dark matter tells you basically how powerful those active galactic nuclei are. So yeah, really good question.
What does this work tell us about dark energy?
Right. So I was a bit schematic about this. And so what does this tell us about dark energy? You may know that measuring the matter distribution in the universe, how it's clumped together, is one of the best way to measure this dark energy. And you can do this in two ways. One is to look at how galaxies are clumped, but it's tricky because of that problem that light and mass don't trace each other so well. The other way is gravitational lensing, and that's presumably the cleanest way in the sense that you're really looking at all of the mass in the universe. The problem though is when you measure that mass distribution in the universe, you need to know how much of it is normal matter versus other source of matter. And since most of the matter is in the form of the gas, if you don't know where it is, that's basically the main limiting factor in doing this. So the way this tells us about dark energy is somewhat indirect, but by telling us where the gas is, you know where the ordinary matter is, and now you can use gravitational lensing measurements to learn about dark energy.
I have a question about the galaxies that you chose to include in your stacking. Did you do any selection for position and orientation of the ecliptic?
Yeah, so we didn't select our sample in any way in terms of orientation, but the way the sample was selected is to be bright, massive red elliptical galaxies. And so yeah, the selection of the sample in that sense is very important. So that's a very good question. And yeah, looking at those bright, massive galaxies is useful because it lets us trace galaxy groups, because that's where those galaxies live, and therefore see more gas.
Any concern that you lost maybe some shape of the gas surrounding the galaxy by doing so?
Right. Yes.
Because you got that nice circle around an elliptical galaxy, and that's surprising.
That's right. That's right. So in presumably, if you look at every individual galaxies, like you're saying, I'll get there. Yeah, if you look at any individual galaxy, it has some elliptical shape. And so you might think, presumably, the gas also has an elliptical shape. And so in practice, I think we know the gas is a bit more spherical than the galaxy itself, but it should have an ellipticity. And ideally, you'd be interested in measuring it. Unfortunately, because we have to average over so many galaxies, we averaged out this orientation. And so that's why we end up with a roughly spherically symmetric gas profile. But if you have more signal to noise and you're able to do the measurement without stacking, then you'd be able to see that.
So build a bigger telescope is what I'm hearing.
Yeah, so you could do that. One problem, again, is that our noise is the cosmic microwave background itself. And so what that means is for an individual galaxy, no matter how well I measure it, I will be affected by this. And so that's why it's hard to do without this stacking. But yeah, it's a very good point.
I have a question about the cosmic background, microwave background. In my lay understanding, when I read, they talk about the fact that before the CMB, light was not present. There were no photons, or they were in a cloud and they could not go out. So why is it that there were no photons before the CMB?
Right, so that's a very good question. So before the time the CMB was emitted, there actually were a lot of photons. And at some time early before the CMB, actually the photons were the main component in the universe. There were just so many of them. But because the universe was so dense and hot, because the universe expands, but if you go back in time, it contracts, it gets dense and hot. Because the universe was so dense and hot, the photons could not freely propagate in the universe because the universe was so dense and hot that there were many free particles and photons would bounce off of them. And so basically what happens at the time the cosmic microwave background was emitted is that after enough expansion, the universe becomes dilute enough that the photons were now able to travel freely and then reach us today. But so basically there were a lot of photons. In fact, the universe was so dense, there were so many photons and free particles that they couldn't travel far. It was like a very opaque, bright soup.
So does that mean that there is a level of density and heat that becomes like a limiting factor for the propagation of photons, and that limit was lifted at that level of expansion?
That's exactly right. That's exactly right. And the way this limit works is that if you start from a very hot, dense soup and the photons can travel far, when you expand it and cool it enough, what happens is that the electrons and the protons in that soup combine into neutral atoms.
Okay.
And the reason that's important is because neutral things don't interact with light the same way. And so as soon as the matter becomes neutral, that's when the light can propagate freely. And so it's really a sharp transition when that happens. Yeah.
Interesting. Thank you.
Thanks.
Anybody else? Don't be shy.
I was actually sitting here trying to remember the term, whether it be heliopause, heliosphere, so on and so on, but I kind of remember that one portion of the sun's influence reaches out as far as, say, halfway to the next nearest star in our system. When you do this type of measurements from clusters of galaxies, is it possible you can find gas doing the same thing, being coming from one galaxy and at least going as far as halfway to the next nearest galaxy? You see what I'm saying?
Mm-hmm. Yeah, actually, that's a really, really good question, and that's a topic of research currently. We call it the two-halo term, but that doesn't matter. The point is, when we measure the shadow of one galaxy, there's often other galaxies around that have gas and therefore their own shadow. And so currently with our sensitivity, when we look at the shadow, we mostly only see the shadow from the galaxy at the center of our image. But if we, when we have more galaxies, which should happen within a year, we should start to be able to see the shadow from the neighboring galaxies. And that's both an interesting thing and a complication. It complicates things because now the shadow is no longer just the gas profile of the galaxy I want. It's a mix with the others. But it's also interesting because it tells me about how the gas in the universe clumps between galaxies. So yeah, it's a really good point, and that's actually something we're trying to measure.
One more question. So I know this gas is very diffuse and everything, but if you found all this gas around all this galaxy, would that account for some of the missing mass that to say is made up of the entire universe rather than just dark matter and dark energy? Does this fraction, whatever it does add to subtract from those two numbers and add to the other number? You see what I'm saying?
Right. That's a good question. So it turns out there's no way really to get rid of dark matter by counting this gas.
Oh, I would say that. Yeah, I know that. Right.
Right. Because so that gas I said was 90 to 95% of the ordinary matter, but the ordinary matter is only about 1/5 of the total matter. Right. And so you can't get rid of the dark matter this way.
Right. No, I wasn't saying get rid of it. I was just saying you took some type of small fraction of percentages of visible, of actual true matter compared to the other types of matter,
Right.
including this diffuse gas,
Right.
making up the total mass of the universe.
Yeah. So that's a good
Right.
point. So when people say, here's the fraction of dark matter versus ordinary matter, this is a quantity you can actually measure from this cosmic microwave background. And that's sort of the source of this missing baryon problem, is when you look at the cosmic microwave background, you see how much ordinary matter there is. And now if you look at a galaxy and count the stars, you see that you only have 5% of that ordinary matter. And this is what people have been called the missing baryon problem, or the missing ordinary matter problem. And this is why, even before measuring this shadow, we knew there should be gas there. And that's what motivated us to look at it. But yeah.
I was also reading recently about these gigantic voids within the universe. There's huge void between there's whether you find really no galaxies or galaxy clusters or galaxy superclusters and so forth and so on. And I'm just saying, now how can they not count that in the mass of the universe?
Right. Yeah. And that, yeah. So that all is important, and it's counted. And yes, on this computer simulation, each bright dot would be a galaxy, and indeed, you have wide spaces empty of galaxies, those voids, and they are important. Yeah.
Right.
I have another question. This one again may be naive, but is there a tie-in between exotic matter and dark matter, or dark energy, relative to warp drive? Okay, the type of energy that's needed to travel faster than the speed of light.
Yeah, that's a good question. Actually, I don't know too much about this. What I can say is that, so we have our current standard model of the universe has those two components, dark matter and dark energy. And the reason we know about them and their effects on the universe are very different. So dark matter is basically just mass that we don't see, other than through effects like lensing. And dark energy, on the other hand, is sort of the opposite of that. It's a force that pushes things away, makes the expansion grow faster. And then I don't know too much about warp drives and how that would be linked, but that's a very good point. Yeah.
That's the Mexican fellow, Aquilbier. He came up with that and says exotic matter. And I was wondering, exotic matter basically is matter that is not made up of protons and electrons. And if there was a tie-in, it would be nice if we could find exotic matter and we could actually go faster than the speed of light. But again, I told you it's probably a naive question, but I thought I'd ask out of curiosity.
There's no naive question. So that's great.
My wife's been cleaning up a corner of the bedroom, and I think she found some of the missing baryons. Whether she's found exotic matter is another matter entirely.
Well, that's helpful, and you know where to post your results.
Absolutely.
I always thought that's where the socks went when they went into the dryer and disappeared. I thought that's where they all went. Right.
Right. Does anybody else have a question for our guest? Well, Manuel, thank you. Let me just do one thing, and that is check YouTube to see if there are any.
No, nothing up there.
There's nothing there? Okay. Well, in that case, thank you very much for traveling all the way to suburban Philadelphia via Zoom.
Well, thank you so much for having me. It was really fun to attend the members meeting and to present to you. Hopefully that was interesting.
Yes, it was. Thank you.
It was indeed. And now you get to eat dinner. We've already eaten on the East Coast here. Thank you.
All right. Well, thank you very much.
I would like to mention that the balloting system that is now on the DVAA website will go live tomorrow, so you can vote in the election. There are no mail-in ballots. There will be no lawsuits about this election. I guarantee you that. I haven't let Rudy Giuliani even know that it's happening. So everything's done on the website, but you do have to be a member in good standing. So make sure you re-up and vote for our slate. And if you wish, come to our meeting, our business meeting on the 13th. That's from 1 o'clock to 4 o'clock. I scheduled it that way because I wanted to be able to see the New Orleans Saints beat the hell out of the Eagles, because anybody who plays them wins. And what we typically do now is we end the recording on YouTube. So I'll count on Jeremy to do that. And we do the equivalent